Your geometric unity paper is 69 pages long, extremely complex, way over my head. So we did what everyone in my position does these days. We went onto YouTube and saw if we could find anybody who'd analysed it and had a conclusion. And we found this. Now, Eric, there's lots of people doing stuff like that about it.
The good news is I have read Eric's paper. Here it is. I actually have it here, right here. And it's worse than you would think. Look, I mean, I didn't say anything about Eric as a person, his history, or anything like that. I said things about the paper. Everything he says about me is like 90% true, as many things he says. The paper is not giving us any reason to think that this approach is promising. There is no quantum mechanics in the paper. There's no attempt at showing that this solves any of the known problems of quantum gravity. Again, it's not just about Eric, it's about anyone. If you want to make an impact on the physics research community,
you either got bars or you don't.
You have to give them a reason to think that what you do is promising.
Bonjour tout le monde. Welcome back to episode 40, I do believe. It's either 40 or 41 now, but either way, in the previous episode, I basically talked the entire time about, well, you know what it is if you saw the last episode. But that was like an hour and a half, and then at the very, very tail end, I was like, okay, now I'm going to actually read the section that I said I was going to read directly from Differential Geometry by Erwin Kreisig. That's the book that I've been reading this whole time in this series, if you haven't figured it out yet. But like I said, this is, chapter 7, chapter 8? Either way, it's the last chapter, and I'm in section 81 and 82. And, right, like in last episode, I, gave the definition of minimal surfaces. I laid out a step-by-step procedure for finding the principal curvatures. And then I was like, okay, you could either multiply all the principal curvatures together and you get Gaussian curvature, which is interesting because then, Riemann goes and builds upon that. Or you could take the arithmetic mean of the principal curvatures in order to get the mean curvature. And when mean curvature is 0 on like a submanifold or a subsurface of what you're given, then that is a minimal surface. It could apply to the entire surface, but not necessarily. And the big nominal example of like a physical real world minimal surface is the soap film when you're given a particular geometry of a wireframe, let's say that the soap film is on. And I was like, okay, now you can go read about geometric measure theory, and then that's kind of like where the rabbit hole on like the soap films took off. But like in this section, which I am going to read out loud today on screen, hopefully 2 sections, they're pretty long when you include the problems and the solutions, but it's important because like I said in the last episode, section 81, you've got 3 theorems basically. One is that you have the catenoid and the right helicoid, which each are unique minimal surfaces within their respective classes. So a catenoid is classified as a surface of revolution. And if you look at all of the surfaces that are classified as a surface of revolution, you look for all of the minimal surfaces, so all of those that satisfy having this 0 mean curvature. Turns out there's only one unique type of surface of revolution that is a minimal surface, which is a catenoid. And then same thing goes, along the same lines for the right helicoid. And this time for the right helicoid, we classify that as a right conoid. So then again, if you get all the right conoids out there together in set theoretical, you lay it all out mathematically, right? And then you're like, okay, well, which ones are minimal surfaces? You only get right helicoids out of that. But then that's where the third theorem comes in, which is 81.3, which I'm going to get to finally today, we see that catenoids and right helicoids are isometric, and therefore that shows that a catenoid can be bent into a helicoid. And then the problems investigate that further. So you find representations of right helicoids which are isometric to a catenoid. That's the first problem. And then in the second problem, it's kind of like, oh, just explore the mapping of the smallest circle of the catenoid to the helicoid. Well, it maps to the helicoid's axis. It goes a little further than that, but I was doing a little more reading, and I'm going to give a little summary about section 82 here in just a sec, but it's like you can kind of get the idea that these sections are another place where complex analysis and differential geometry meet up. So the last time that this really, comes to mind for me is with the Bergman kernel, Bergman metric stuff. There was, the complex analysis kind of peeked its head a little bit there, but it's really going to come up in the next two sections. So I was reading Visual Complex Analysis. I've brought up that book before. Where is it? It's right behind me. Right here. It's the blue one. And when you think about the catenoid and the right helicoid, yeah, they're minimal surfaces, but if you look at this in terms of complex variables, it actually makes the relationship between those two surfaces a little more clear, I think. So, okay, I hope this is still recording, but anyways, I didn't type this up in LaTeX, and I didn't, write out like 10,000 words of a script here. The only verbatim script that's going to happen today is when I actually read from this book, finally getting back to it. But, okay, so these notes here, this is from the very beginning of chapter 12, and so there's like a lot more context, it seems like, to this stuff in the previous chapter 11 to this, but the gist of it as follows. So let capital H over bar equal to capital omega prime over bar be a steady sourceless irrotational vector field with complex potential omega equals capital phi plus I capital psi. I believe that's what those are, and that's how you pronounce those Greek characters. I botched that so many times in this series that we're just going to keep going forward here. If at each point we rotate capital H over bar through a fixed angle, that's just a theta, then we obtain the so-called polya vector field of the analytic function capital H sub theta, which is equivalent to complex exponential e to the power of negative I theta, and then that complex exponential is times capital H. Namely, we have that capital H theta over bar equals I times e to the I theta, then times capital H over bar. Thus, this rotated vector field is automatically sourceless and irrotational, and its complex potential is omega sub theta equals e to the negative I theta, then times omega. And writing omega sub theta equal to phi sub theta plus I c sub theta, then the potential and stream functions are phi sub theta equals cosine theta times phi plus sine theta times c, and c sub theta is equal to cosine theta times c minus sine theta times phi. In particular, when you have theta equal to positive pi over 2, the positive is a critical distinction, and that's a special case where the polya vector field we can denotate here. Capital H sub pi over 2, we're going to denote that as capital H wedge over bar. When we denote the whole capital H with the wedge over bar, and we then furthermore consider what capital H wedge over bar, then itself with an over bar means, that is equivalent to capital H sub pi over 2 over bar, which is furthermore equivalent to I times capital H over bar. Thus, if you see what's going on here, if you know about complex variables, then you know that complex conjugation is when you negate the imaginary part of the overall complex value, right? But you keep the real part. And so the conjugate, as a result of doing that, is going to be orthogonal to your original. But it's that's why we have the distinction of theta being positive pi over 2. Because, okay, that whole capital H with the wedge over bar in addition to another over bar being eventually equal to I times capital H over bar, that's not what I just said of like technical what actual complex conjugation is, where you just negate the imaginary part. But that means that the capital H with the wedge over bar and the additional over bar operator, that is still like conjugate in terms of being like, you know, you could look at it as like maybe like geometric conjugation more generally. But anyways, at this point in the visual complex analysis book, they refer to that whole complicated, I'm not going to say complex because we're talking about complex analysis. So if something is complicated, you need to say complicated and not complex. But anyways, capital H wedge over bar in addition to another over bar, that's just going to be called the dual of capital H over bar because of, like I just said, it's, you know, take I times capital H over bar and you get the dual of H, essentially. But this is leading up to the punchline. Thus, the potential and stream functions are the dual potential and dual stream functions, respectively. But then there are two miracles as a result of this in what was I originally talking about? Minimal surfaces. So the first miracle is each complex analytical function, say capital H of a complex variable z, describes the shape of a minimal surface and vice versa, meaning all minimal surface shapes can be described by complex analytical functions. Second miracle then is that varying this theta causes the minimal surface corresponding to capital H sub theta of z to undergo stretch-free bending, and all these minimal surfaces have identical intrinsic geometry. Therefore, the example in visual complex analysis, I'll probably paste a picture on the screen, hopefully now, is that if this function, the complex analytical function you start off with, corresponds to a helicoid, then the dual of that corresponds to a catenoid. So yeah, eventually we're going to get to the third problem, or second problem in section 81. And I don't think that what I just said is brought up. It's a completely different exploration. So I don't know, it's a little bit of foreshadowing. Okay, and then in section 82, we're going to introduce the so-called Weierstrass representation, or the Weierstrass-Enneper representation, which is obviously named after Karl Weierstrass, who is regarded by many as the father of analysis, and perhaps rightly so, because among many other contributions to trailblazing formal modern analysis as we know it, one of the things that he did was he formalized and originally applied the epsilon delta definition of a limit, which everyone who's watching this video, if you don't know what that is, I don't know how you're watching this far into this video, honestly. It's like everybody knows what the epsilon delta definition of a limit is. Just, I mean, here's another like pop trivia about Weierstrass that maybe some of you might not know, but there's the Weierstrass function, which is a real valued function that is continuous everywhere but differentiable nowhere, and is an example of a fractal curve. You can look up a picture of it, but it's really relevant as far as like a counter example of analysis. It's really important sometimes to know when, or have examples of a function that's continuous everywhere and also differentiable everywhere, but also, for example, with the Weierstrass function, it's continuous everywhere, differentiable nowhere. Anyways, all those counterexamples kind of sharpen your understanding of the definitions, the tools that you have to use. But the Weierstrass representation is not one of the ones on his Wikipedia page at the top, though. You know what I mean? What else is here? And I guess looks like the problem for section 82 is just finding the Weierstrass representation for the right helicoid. Anyways, at some point I'm probably going to define complex holomorphic functions, complex Laplacian, complex harmonic functions, meromorphic functions, but this is a lot already. Boy, this is going to be quite an edit. Hopefully you guys can see. Oh, this cat is going to attack me. This cat's pissed. Okay. Anyways, section 81. This cat is just like... He's pissed. He's like, what are you doing right now? Anyways. Section 81. Examples of minimal surfaces. Look at him. He's like... Okay. He's mad. Okay. Section 81, examples of minimal surfaces. Surfaces of revolution and right conoids were introduced in Section 28, which was the previous section on properties of the first fundamental form. We will now see that each of those two classes of surfaces includes exactly one type of minimal surface, namely the catenoid and the right helicoid. These two types of surface, which look entirely different in the embedding space, are even isometric. We will see that a catenoid, when cut along a meridian, can be isometrically mapped into a suitably chosen right helicoid. The principal normal surface of a circular helix, for which we can refer back to section 8, which is examples of special curves, and look at where we are now, here in examples of minimal surfaces at the very end of the book. But the principal normal surface of a circular helix is called a right helicoid, and this surface can be represented in the form vector x in terms of u1 star and u2 star is equal to, in the first entry of 3 total entries, u2 star then times cosine of u1 star, and then in the second entry, u2 star then times sine of u1 star, and then in the third and final entry, c times u1 star. And this is therefore a special right conoid, for which we can refer back to problem 28.2, which stated a surface capital S is called a right conoid if it can be generated by a moving straight line capital G intersecting a fixed straight line capital G naught, so that G and G naught are always orthogonal. Find a parametric representation of a right conoid and determine the corresponding first fundamental form. And now we come to theorem 81.1. Right helicoids are the only right conoids which are minimal surfaces. The proof is as follows. From the general local representation of right conoids, namely, the vector x in terms of u1 star and u2 star is equal to, entry-wise, u2 star times cosine of u1 star, and then u2 star times sine of u1 star, and then h of u1 star, we thus obtain that we have the following components and discriminant of the first fundamental form. So we have g sub 1 star equals u2 star squared plus h prime squared, and then g12 star equal to 0 and g22 star equal to 1, and g star, the discriminant of the first fundamental form, equal to u2 star squared plus h prime squared, where a prime denotes the derivative with respect to u1 star. Now, from expression 34.1, which is just the expression of a unit normal vector, namely, vector n is equal to a fraction with a numerator of vector x1 cross product with vector x2 all over a denominator of the magnitude of the cross product of x1 with x2. This then is in turn equal to another fraction where the numerator is vector x1 cross product with x2 all over a denominator of the positive square root of g being the discriminant of the first fundamental form. From this, we find the following representation of the corresponding unit normal vector. Namely, n, that vector, is equal to 3 entries, the first being negative fraction with the numerator h prime times sine of u1 star all over a denominator of the square root of g star. Then the second entry of the unit normal vector is h prime times the cosine of u1 star all over a denominator of the square root of g star. And then the third entry is the negative fraction of u2 star all over a denominator of the square root of g star. Hence, because of what is expression 38.2, which is just simply a statement of the second fundamental form, basically b sub alpha beta is equal to vector x sub alpha beta, then scalar product with the unit normal vector n, where that x sub alpha beta vector is really the product of some partial derivatives with respect to x alpha and x beta coordinate directions. So hence, because of 38.2, b sub 1 star is equal to the negative fraction u2 star times h double prime all over the square root of g star. And then this is, like I said, this is a component of the second fundamental form. B sub 2 star is equal to h prime over the square root of g star. And then b sub 2 star is equal to 0. And therefore, by 41.10, which is just the definition of mean curvature, we have that capital H, which I know in the beginning I was talking about capital H of z being like, this complex function, but we can just throw that out the window because throughout this book, capital H has always been mean curvature. So capital H mean curvature now is equal to negative fraction with the numerator u2 star times h double prime all over 2 times g star, which is to the power of, that looks like 3/2. It's like if you got a good PDF, that's awesome. But sometimes you run into stuff like this where you're like, oh no, I really wish I had a physical book in order to verify what these little tiny exponents really are. It's actually 3/2. So like I thought. Then we have figure 84, which is of a catenary. That's what you rotate the catenary about an axis in order to obtain the catenoid. Catenary turns into a catenoid that way. So moving on, in order that the right conoid be a minimal surface, namely where mean curvature capital H is equal to 0, we must have that lowercase h double prime is equal to 0. That is, lowercase h must be a linear function of u1 star. This means that the right conoid must be a right helicoid. We now consider surfaces of revolution, the curve which a perfectly flexible chain of homogeneous mass distribution with fixed endpoints assumes under the action of gravity is called a catenary, which is what I just mentioned. Well, that's not what I said, but I just referred to in figure 84. As follows from the differential equation corresponding to this problem of mechanics, the catenary can be represented in the form r of x equals a times hyperbolic cosine of b times x minus c. When the catenary is rotated about the x-axis, it generates a surface of revolution, which is called a catenoid, which is depicted in figure 85. Moving right along, we are at theorem 81.2. Catenoids are the only surfaces of revolution which are minimal surfaces. The proof is as follows. Every surface of revolution, not a cylinder, whose axis is the x3 axis of the Cartesian coordinate system in space, can be locally represented in the form x3 is equal to a function q in terms of radius r, and r squared is equal to x1 squared plus x2 squared. We have a Pythagorean theorem there. So by writing u2 instead of r and choosing a parametric representation in the form vector x in terms of u1 and u2, I refer to them as coordinates throughout this, but anyways, equals 3 entries, first entry being u2 then times cosine u1. Second entry is u2 times sine of u1. Third entry is function lowercase h in terms of u2. Below we have the figure 85 depiction of a catenoid. Consequently, because of this parametric representation that we were just discussing before we hit the catenoid figure here, we have the following components and discriminant of a first fundamental form, correspondingly, or consequently, anyways, g sub 1 equals u2 squared. Then we have g sub 1 2 equal to 0, and then g sub 2 equal to 1 plus h prime squared, and finally, the discriminant, just lowercase g, is equal to u2 squared, then times the quantity 1 plus h prime squared, lowercase h that is, where again a prime denotes the derivative with respect to u2. Furthermore, we obtain second fundamental form components, namely b sub 1 1 equals negative fraction with a numerator of u2 times h prime all over a denominator of the square root of the quantity 1 plus lowercase h prime squared, closed quantity. Continuing on, b sub 1 2 is equal to 0, and b sub 2 2 is equal to the negative fraction with the numerator of lowercase h double prime all over the square root of the quantity 1 plus lowercase h prime squared, closed quantity. For all this, we can refer back to problem 40.1. And you may say, why problem 40.1? Well, that's because in that problem, we found the differential equation of the asymptotic curves of a surface of revolution, which had, if I'm not mistaken, strikingly similar components to 81.2, and we determined the location of elliptic, parabolic, and hyperbolic points on that surface. So, we had already found the first and second fundamental form components in order to do that, because if you remember, maybe I'll put the table from the formula sheet on the screen now, but judging upon, if some of those are positive, negative, or zero, you can classify them as elliptic, parabolic, or hyperbolic points. I forgot what the classification is, honestly. I don't know what it is off the top of my head, but it's on the screen, or was. Anyways, since g sub 1 2 equals 0 and b sub 1 2 equals 0, the coordinate curves are lines of curvature on the surface of revolution, for which refer back to 41.6. That expression, which is being referenced here, actually is part of theorem 41.3, which states that the coordinate curves of any allowable coordinate system on a surface, capital S, let's say, coincide with the lines of curvature if and only if for this system g sub 1 2 equals 0 and b sub 1 2 equals 0 at any point where those coordinates are allowable. So that's basically what we just ran into. Consequently, this is thick with references here, but by expression 41.11, which is just the definition essentially of Gaussian curvature, which is denoted capital K throughout this book, and mean curvature, capital H, as again it's denoted throughout this book. It gave those in terms of components of the first and second fundamental forms. So of relevance here is obviously mean curvature, and so that's capital H equals 1/2 times the quantity b sub 1 1 over g sub 1 1, then plus b sub 2 2 over g sub 2 2, closed quantity. So consequently by that, and that's actually looks like, like the left-hand side here of what we've got going on in front of us, capital H is equal to 1/2 times the quantity b sub 1 1 over g sub 1 1 plus b sub 2 2 over g sub 2 2, closed quantity, which in this specific case of what we're working out here is equal to negative 1/2, then times the quantity where we have first a fraction, lowercase h prime over a denominator of u2, then times the quantity 1 plus lowercase h prime squared, closed quantity, but then that quantity is to the power of 1/2, and then plus now the second fraction within this overall quantity, which has the negative 1/2 on the outside. We have the second fraction numerator being lowercase h double prime all over a denominator of the quantity 1 plus lowercase h prime squared, closed quantity, to the power of 3/2, where that 3/2 is only on the quantity in the denominator of that second fraction, which now we're going to close the overall outer quantity. So if the function lowercase h of u2 is constant, we obtain a plane parallel to the x1, x2 plane. This case is not of interest. If, on the other hand, lowercase h prime is non-zero, the condition where capital H, mean curvature, equals 0 implies that we have a fraction numerator being lowercase h double prime times h single prime all over a denominator lowercase h prime squared, then times the quantity 1 plus lowercase h prime squared, closed quantity, is then equal to negative 1 over u2. Therefore, we set lowercase h prime squared equal to, let's say, lowercase w, then 2 times lowercase h single prime, then times lowercase h double prime. This equals lowercase w double prime, and from the preceding relation, we have a fraction w prime over a denominator of w times quantity 1 plus w closed quantity. This is then equal to negative 2 over u2, or in other words, we could have a quantity 1 over w minus 1 over 1 plus w closed quantity then times dw, which is thus equal to negative 2 over u2 then times du2. So we're introducing those infinitesimal dw and du2s there. Doing a little factoring on that fraction, a little bit of algebraic manipulation there. Integrating this equation, we find that we have the log of w over 1 plus w, which is equal to negative 2 times the quantity log u2 minus c closed quantity, which is equal to the log of the fraction c squared over u2 squared. This equation is equivalent to lowercase h prime squared over 1 plus lowercase h prime squared, which is equal to c squared over u2 squared. That is, lowercase h prime is equal to a fraction of c over the square root of the quantity u2 squared minus c squared closed quantity. Integrating once more, we finally obtain lowercase h equals c times the inverse hyperbolic cosine of u2 over c, and then minus c tilde. And we also have, or that is to say, u2 is equal to c times hyperbolic cosine of fraction x3 plus c tilde all over c. This means that the meridians of our surface of revolution of vanishing mean curvature are catenaries, and consequently the surface is a catenoid. We will finally investigate the isometry of the right helicoids and the catenoids. Theorem 81.3. The catenoid defined by the previous expressions 81.2 and 81.5 can be isometrically mapped onto a portion of the right helicoid, which was given in the expression 81.1. The proof is as follows. The first fundamental form corresponding to the expression of a right helicoid is given by the expression ds star squared is equal to the quantity u2 star squared plus c squared closed quantity then times du1 star squared plus du2 star squared. For the catenoid, we have ds squared is equal to u2 squared then times du1 squared plus a fraction of u2 squared over u2 squared minus c squared, and then this fraction is times du2 squared, for which we can refer back to the expression that I just read of 81.4. Furthermore, setting u1 star equal to u1 and u2 star equal to the square root of u2 squared minus c squared, we have that du1 squared is equal to du1 and du2 star is equal to u2 over the square root of u2 squared minus c squared, then times du2. And the first fundamental form, which was at the beginning of the proof of this theorem, becomes identical with the ds squared expression that followed it. By means of these relations, we introduce u1 and u2 as coordinates in the right helicoid. The mapping under which any point of the right helicoid corresponds to the point of the conoid with the same values of the coordinates u1 and u2 is then isometric in consequence of Theorem 57.1, which, as a reminder, Theorem 57.1 was that an allowable mapping of a portion capital S of a surface onto a portion capital S star of a surface is isometric if and only if at corresponding points of S and S star, when referred to the same coordinate systems on S and S star, and within this theorem it's saying refer back to section 56, which is preliminaries of the mappings, which is the preliminaries section of the mappings chapter 6. The coefficients of the first fundamental forms on these portions S and S star are the same, namely G sub alpha beta equals G star sub alpha beta for alpha equals 1 and 2 and beta equals 1 and 2. This mapping can be realized by bending, and we'll see that in figure 86 when I turn the page here. We cut the catenoid along the meridian where coordinate u1 is equal to 0 and bend it until it coincides with the pitch of the right helicoid under consideration. Since the curves where u1 is equal to a constant are meridians of the catenoid, and the curves where u1 star is equal to a constant are generators of the right helicoid, the meridians are mapped onto straight lines on the right helicoid. Wow, that was a tricky sentence. The images of the parallels where u2 equals u2 naught, which are equal to a constant of the catenoid, are arcs of the circular helix, where u2 star equals u2 star naught, which is equal to the square root of u2 naught squared minus c squared, which is equal to a constant. In particular, the smallest of the parallels, where u2 equals c, is mapped into the axis of the right helicoid, which we see in figure 86 above. It can be proved that all the surfaces occurring in connection with the bending of the catenoid into the right helicoid are minimal surfaces. They are called minimal surfaces of Shirk. And go figure, we can read all about that in Shirk's work. And we have come to the problems. I'm back, you guys. It's the next day. Alright, so I'm going to get back to reading the problems and their solutions from section 81. Starting with problem 81.1. Find a representation of the right helicoids which are isometric to a catenoid. And we're going to remind ourselves real quick of problem 57.1. As a matter of fact, problem 57.1 is a proof of the preceding theorem 57.4, which is Bohr's theorem. Not sure how to properly pronounce that, but at any rate, that states that for every right helicoid, capital S, there exist surfaces of revolution which can be mapped isometrically onto that helicoid. And so problem 57.1 is just to prove that theorem. All right, the solution of problem 81.1. If u1 equals a times the hyperbolic cosine of x3 over a is a representation of the meridian of the catenoid, this surface may be represented in the form, a vector parametric form that is, of the vector x in terms of u1 and u2 equal to 3 entries, where the first entry is u1 cosine u2, the second entry is u1 sine u2, the third entry is a times the inverse of the hyperbolic cosine of u1 over a. Then we have, this is actually going to be referred to momentarily, so we have expression alpha here, which is ds squared equals a fraction first, which is u1 squared over a denominator of u1 squared minus a squared, and then that fraction is then times du1 squared, which is then plus u1 squared times du2 squared. And it says here we may use the answer to problem 57.1 from equation 3 in that problem, which actually, like I was saying, doesn't have to do with the first or second fundamental forms of a helicoid, as I was guessing. But that expression that was referenced just now is u1 squared equals nu squared times the quantity u1 star squared plus c squared closed quantity. So as a result of that, then we now obtain, getting back to problem 81.1, we have that basically the ratio of du1 to du1 star is equal to nu squared times u1 star over u1. I guess I didn't write this one down, but from problem 57.1, we have this statement towards the beginning of the solution, which is ds squared equals quantity 1 plus lowercase h prime squared closed quantity then times du1 squared plus u1 squared times du2 squared. And so now getting back to problem 81.1 solution again, it's saying if we compare that to this expression alpha that I just read above, we have 1 plus lowercase h prime squared equals a fraction of u1 squared over a denominator of u1 squared minus a squared. Hence, if we replace u1 according to the expression 3 from the solution of problem 57.1, then the left-hand side of, so back in the solution for problem 57.1 again, we have the expression 4 within the solution in the back of the book here is quantity 1 plus lowercase h prime squared closed quantity then times another quantity which is the fraction of du1 over du1 star closed quantity then squared, which in turn is equal to 1 plus the fraction of a numerator u1 star squared then times capital G prime squared all over a denominator of u1 star squared plus c squared. So the left-hand side of that takes the form of a fraction with a numerator nu to the fourth times u1 star squared, and then a denominator of nu squared times quantity u1 star squared plus c squared closed quantity minus a squared. And going back again to expression 4 from the solution of problem 57.1, that can be solved for capital G prime, and we furthermore set nu equal to 1 and a squared minus c squared equal to, let's say, k squared. Then we now have that capital G is equal to lowercase k times the integral of the square root of a fraction with the numerator u1 star squared plus c squared all over a denominator of u1 star squared, then times the quantity u1 star squared minus k squared, and that closes the square root, and the integral then is du1 star. So we can then continue to compute capital G, which is thus lowercase k times the logarithm of, first we have the square root of the quantity u1 star squared plus c squared closed quantity plus, and then we have a second square root within this logarithm, which is the square root of u1 star squared minus k squared. That closes the second square root as well as the logarithm, because then that k times the logarithm of those two square roots is then minus c times the inverse tangent of k over c, and then times, presumably outside of the inverse tangent, we have a square root of a fraction where we have in the numerator u1 star squared plus c squared, and in the denominator we have u1 star squared minus k squared. So because we've now computed G, we've set the constant of integration equal to 0. This constant corresponds to a displacement of the right helicoid parallel to the x3 axis. We thus obtain the following representation of the right helicoids, which are isometric with the given catenoid. And it says here to refer back to problems 28.5 and 35.1. And to refresh our memories here, problem 28.5 states, if a twisted curve capital C rotates about a fixed axis capital A and, at the same time, is displaced parallel to capital A so that the velocity of displacement is always proportional to the angular velocity of rotation, then the twisted curve capital C generates a surface capital S, which is called a general helicoid. And the problem asks, find a parametric representation of capital S, the surface. And then problem 35.1 was introduce orthogonal coordinates on a general helicoid capital S such that the helices and their orthogonal trajectories on S are coordinate curves. And funny enough, that problem says to refer back to problem 28.5. So this is kind of like a series of problems that's been going on from much earlier in the book. So continuing on, we were able to pull results from those problems. You can go back to previous episodes because I've read every single problem and solution basically after like problem 7 in the very beginning of like the theory of curves chapter. That was the asking ChatGPT an easy differential geometry problem. So there's like 6 problems in the very, very, very beginning from the preliminaries that I skipped basically. Every other problem and solution I have read out loud in these differential geometry reading stream series episodes. So you can go back and you can rewatch and find problem 28.5, problem 35.1. If I have my act together, then I'll have links for those, on the screen in the description. But no guarantees, but anyways, we're getting back to this. This next expression is going to be referenced in the next problem from this section, which is section 81. So we have, without any further ado, expression beta, which is a vector parametric representation of this catenoid, presumably where it is a vector called x in terms of coordinates u1 star and u2 star. And the representation has, of course, 3 entries, and I'm going to read them entry-wise now. First entry is u1 star times cosine of u2 star. The second entry is u1 star times the sine of u2 star. And then the third entry is c times u2 star plus capital G of u1 star. And it continues on here where capital G is defined by the preceding formula. The pitch 2 pi times c can be arbitrarily chosen. If we choose c equals 0, we obtain the given catenoid. If c increases, the pitch increases. If c equals a, that is k equals 0, we obtain the right helicoid with a vector parametric representation of x in terms of u1 star and u2 star equal to entry-wise u1 star times cosine u2 star, and then u1 star times sine of u2 star, and then c times u2 star. This proves that a catenoid, which has been cut along a meridian, can be bent onto a pitch of the right helicoid. All right, problem 81.2, and this is the last one for section 81. Investigate the behavior of the smallest circle of the catenoid when the bending represented in the above figure 86 on this page here is performed. Use the results of problems 57.1 and the previous 81.1. So we already read and reminded ourselves what problem 57.1 was. We just did the solution to problem 81.1. So let's just get right into this one. And this one is a nice little short one, relatively speaking, of course. The solution of problem 81.2. The smallest circle, capital C, say, is given by u1 equal to a, and we can refer back to the notations in the answer to the preceding problem 81.1. If we insert this into equation 3 of the answer to problem 57.1, we've already discussed this, so maybe I'll have a reminder on screen. But continuing on, if we also set nu equal to 1 and obtain u1 star squared equal to a squared minus c squared. Now, this is where it's a callback to expression beta, again from the previous problem solution. Equation beta thus takes the form of a vector x, let's say, in terms of u2 star, which this vector is now equal to 3 entries because it's a vector, obviously. The first entry is the square root of a squared minus c squared, and then this square root term is times the cosine of u1 star. Second entry, similarly, we have a square root of a squared minus c squared, but this time it's times the sine of u2 star, and then the third entry is c times u2 star plus k naught, lower k naught. And we may set this lower k naught equal to 0. So the image of the smallest circle, capital C, is a pitch of a circular helix on a cylinder of revolution of radius lowercase r equals this square root of a squared minus c squared. And the length 2 pi times a of the image is independent, obviously, of c. And the bending illustrated in the figure where there's the catenoid and then it, kind of gets like cut and turned into this like, kind of noodle shape. I don't know what kind of type noodle it is. I'm not Italian, obviously, but anyways, that bending corresponds to an increase of c, this parameter. Yeah, so corresponds to an increase of this parameter c from 0 to a. This is actually a typo in the PDF. In the book, it's correct, though, the physical book that I have, I guess. Amazon affiliate link in the description. So in the course of this bending, the radius r of the above cylinder decreases and ultimately tends to 0. That is, the image of the smallest circle, capital C, ultimately is a segment of a straight line. And if I've done my editing properly, which, that's kind of one of the things that holds this channel down, I feel like is the editing in these videos, if not the content or my personality or anything like that. It's really the editing of these videos. I think that is like the main thing. But if I have my editing game on point with this, then at the beginning I talked about how there's in, I guess, complex analysis, you could call, it's not exactly complex conjugation, but when you have these sourceless irrotational vector fields, complex vector fields, of course, and you do not complex conjugation, but you find the dual of that vector field. If you have, let's say, like, complex valued function, capital H, not to be confused with mean curvature, of course, but you have this complex valued function, capital H of Z, then the dual of that, if you had capital H being a catenoid, then I'm pretty sure that the dual would be the helicoid. Or I got those backwards. Yep, I did. H corresponds to a helicoid. H with that wedge over bar corresponds to a catenoid. That was probably like a 20-minute rant at the beginning. I'm sorry and I'm not sorry, but we're going to go on to section 82 now. All right, so we are back. It is now day 3 of me filming, reading sections 81 and 82 out loud here. And I just want to say, so, right, like this is day 3. I'm going to edit it tomorrow, Friday, as day 4, and I'm going to rush to get it out. Normally, I try to schedule these so that I upload at 8 a.m. on Monday morning. I feel like if I have a really good video, it doesn't matter if I schedule it on Monday, but I'm not trying to say this like, I'm making cookie cutter videos all the time, but if I have a more average video, it actually does make a difference by me uploading it on Monday, because the maybe like 50 views or whatever that it might get from Monday and Tuesday, that makes a difference in building momentum to then get a little bit more views on Thursday and Friday later in the week. And that's, like I said, if it's a good video just in and of itself, because maybe I like did a cinematic intro or something, then, or like a funny clip in the beginning, then that could just pop off if I upload it just straight up on a Thursday or at whatever time during the week. Anyways, but yeah, I feel like after the Mars meditation full-length episode where I was reading 10,000 words that I had scripted over like a month in between uploads, I promised in that video that I was going to read these sections, and so I'm like, you know what, I'm just gonna film this, I'm gonna upload it tomorrow, because like right now it's 5:38, so I got off work and all this stuff, and I'm gonna clean my apartment basically. Anyways, but I don't know why that started, but okay. Section 82, Relations between Function Theory and Minimal Surfaces, the Formulae of Weierstrass. We will now study an interesting relation between minimal surfaces and function theory, which was discovered by Weierstrass. We mentioned already in section 80 that these results had considerable influence on the development of the theory of minimal surfaces. We start from the following, Theorem 82.1. Let capital S be a simply connected minimal surface, given by a representation vector x in terms of coordinates u1 and u2 of class r greater than or equal to 3, where u1 and u2 are isothermic coordinates on the simply connected minimal surface capital S. And we have a reference here to go back and revisit section 62, which is conformal mapping of surfaces into a plane. And continuing on from theorem 82.1, then the components x sub I of the vector function x are harmonic functions. That is, solutions of Laplace's equation. Del of x sub I, that's a delta, but we're saying that it's Laplacian operator. So we have del of x sub I equals 0, or in vector notation, del of the vector x is equivalent to x sub 1, 1 plus x sub 2, 2 equals 0. This is, of course, like one of many different formulations one of the different Pokemon versions of Laplace's equation that you can come upon in the wild. This is also why I said yesterday that I was going to talk about the definitions of holomorphic, harmonic, and meromorphic functions. So I guess, I don't know, I'll just read on with the proof here. The existence of isothermic coordinates u1 and u2 on the simply connected minimal surface, capital S, follows from theorem 62.1, which is, okay, I'm assuming that this is what it is. If it's totally wrong, then I'm going to put it up on screen and I'm going to cut all this out. But otherwise, we have, let capital T be an allowable mapping of a portion capital S of a surface into a plane capital E, and denote by u1 and u2 Cartesian coordinates in the plane capital E. Next, we introduce u1 and u2 as coordinates on this portion capital S. This is different, okay, what I'm going over from section 62 here. This is different from the simply connected minimal surface capital S, same letter from theorem 82.1. So keep that straight for now. If capital T is a conformal mapping, then the first fundamental form on capital S, the portion, from what we're reading in section 62 here, with respect to u1 and u2 is given by ds squared equals nu of u1 and u2, or nu in terms of u1 and u2, then times the quantity du1 squared plus du2 squared, closed quantity, where that function nu is positive. And going on a little further here, we have definition 62.1, which is that allowable coordinates u1 and u2 on a surface capital S for which the corresponding first fundamental form is of the type that I just read, that ds squared equals nu times du1 squared plus du2 squared. When it's of that type, they're called isothermic coordinates on that portion capital S. Because, okay, going back to this, now it's all going to make sense. Because, okay, we're going to read theorem 62.1, definition 62.1. The existence of isothermic coordinates u1 and u2 on S follows from what I just read, basically, theorem 62.1. And we have, like I just read, ds squared equals nu times du1 squared plus du2 squared with positive nu, referring back to what I just read. And lowercase g, which is a discriminant of the first fundamental form, equals that function nu squared. Consequently, g superscript 1 equals g superscript 2 then equals 1 over nu. So these are components of the first fundamental form. Therefore, by 38.2, which is just the statement of the second fundamental form, so you have b sub alpha beta equals vector x sub alpha beta scalar product with vector n, where that x sub alpha beta vector is the product of partial derivative along x alpha and then a partial derivative along x beta, and then n is a normal vector. So by that, that's 38.2, and then and then by 41.10, that is just the definition of the mean curvature of a surface at a given point. You could have it in terms of principal curvatures, so mean curvature is the arithmetic mean of principal curvatures, or it's in terms of the second fundamental form and first fundamental form, basically. But we're going to recapitulate that here. So because of those, we have capital H equals 1/2 g superscript alpha beta then times b sub alpha beta, which equals then what's relevant to this problem, this proof rather. We have 1 over 2 nu then times the quantity b sub 1 plus b sub 2 closed quantity. Those are components of the second fundamental form, like I was saying. That expression is then equal to 1 over 2 nu then times, we have these vectors going on here. We have quantity x sub 1 plus x sub 2 closed quantity, but then that is scalar product with n. And then it turns out this is equal to 1 over 2 nu then times vector n scalar product with del of x. We have a Laplacian of x. It's like second derivative, x direction, plus second derivative in the y direction. So we don't have any, take a derivative in x, then a derivative in y. But, truth be told, right, this is just kind of like a sidebar. A lot of the interesting problems in science and engineering, doing Laplace's equation like this is just baby stuff when you really think about it. And it's humbling, but it's like, now there's just even more stuff that you got to know and that you got to study and be up on in order to apply any of this stuff in the real world. And it's like, if you get bogged down by this stuff, well, it's like, good luck getting to any of the real world stuff. So, anyways, so since capital S here is a simply connected minimal surface, then since capital S is a simply connected minimal surface, that is to say, its mean curvature, capital H, is equal to 0, then we have that vector n scalar product with del of x is equal to 0, and the vectors n and del of x are orthogonal. From what I just read above, the ds squared equals nu times du1 squared plus du2 squared, from that we have that g sub 1 1 equals g sub 2 2. That is, vector x sub 1 scalar product with vector x sub 1 is equal to vector x sub 2 scalar product with vector x sub 2. So that's kind of like what I alluded to with when you define that general component of the second fundamental form, b sub alpha beta equals vector x sub alpha beta. It's basically like, okay, if you recall the definition of what that vector x sub alpha beta is, that's what this is literally breaking down. So by differentiating the scalar products that are equivalent that I just read with respect to the isothermic coordinate u1, which actually do we know it's isothermic yet? We obtain the scalar product of vector x sub 1 with vector x sub 1 1 is equal to the scalar product of x sub 2 with vector x sub 1 2. Furthermore, g sub 1 2 is equivalent to vector x sub 1 scalar product with vector x sub 2, and this is equal to 0. By differentiating this with respect to isothermic coordinate u2, we find that we now have the scalar product of x sub 1 2 with x sub 2 plus the scalar product of x sub 1 with x sub 2 2 equals 0. Hence, by one of those equivalences of scalar products that were on the previous page, we now furthermore have that the scalar product of x sub 1 with x sub 1 1 is equal to the negative scalar product of x sub 1 with x sub 2 2, or in other words, the scalar product of vector x sub 1 with the Laplacian of x equals 0, or the vector Laplacian of x is also orthogonal to the vector x1. By differentiating another one of those previously read equivalent scalar product statements with respect to u2 and the one at the top of the page, the one that's the component of the first fundamental form, g sub 1 2, differentiate that one with respect to u1, now we similarly find that the scalar product of vector x sub 2 with del of x is equal to 0. Therefore, del of x is equal to 0, and this completes the proof. So a nice plug and chug, computing out those scalar products, components of the first and second fundamental forms, right on. Moving on. Every function of two real variables which is harmonic in a simply connected domain, is the real part of a suitable analytic function. Thus, we obtain a relation between minimal surfaces and function theory. Okay, so yeah, I should just read these definitions right now. I'm just going to read them straight off the top. I'm just going to read this one. A holomorphic function, that is to say a complex function, is one that is differentiable at every point of some open subset of the complex plane. And holomorphic functions are analytic, and analytic functions are complex differentiable. Therefore, holomorphic functions are infinitely differentiable. So that's a very nice property. If you know your function is holomorphic, that would be an incentive to try and show some way, because then you get that infinite differentiability. What am I saying here? Continuing on. If f is continuous in... Okay, well, here's an alternative definition of the Laplacian. Well, I guess I didn't even give one. I just, we've been talking about what's Laplace's equation, right? But the Laplacian operator is let f be a complex function in a plane open set capital omega such that the second derivative of f in terms of x and the second derivative of f in terms of y exist at every point of this plane open set capital omega. And the Laplacian of f, that operator, is denoted with a delta symbol. We can call it del. It's consistent with everything I've said up to this point. But going on here, I just had to introduce the notation for the plane open set because, okay, if f is continuous in capital omega, and if the Laplacian of f equals 0, maybe if it's in Laplace's equation, right? Then, and if it's at every point of this plane open set omega, then f is said to be harmonic in that plane open set capital omega. Okay, so that's what it means to be harmonic. Just said holomorphic. We're continuing on here. We're going to connect them together conceptually. Since the Laplacian of a real function is real if it exists, a complex function is harmonic in this plane open set capital omega if and only if both its real part and its imaginary part are harmonic in omega. Furthermore, we have this theorem, and this is from chapter 11 of Papa Rudin, okay? Theorem 11.4 in Papa Rudin, we have that holomorphic functions are harmonic. Okay, so we're getting all these, by introducing definitions of holomorphic and harmonic, we're like, okay, we're referring to something that is a complex function. We can be explicit about, okay, maybe it's not the entire domain. We can constrict it to this plane open set where we have a Laplacian equal to 0, etc. And then maybe you could then say, oh, it's infinitely differentiable. Okay, that's the kind of stuff that we might be wanting to pull out of thin air here. Going on, a meromorphic function on an open subset. We're switching up letters, capital D, that is holomorphic on all of capital D except for a set of isolated points. We call them poles of this function. That is a meromorphic function. Okay, because now, look out, there's a cat in front of me. We're back to this, and we're going to be discussing harmonic functions. We're going to be discussing the Cauchy-Riemann differential equations. Okay, that's another thing I wrote down, but okay, I guess I can't find the stuff that I was going to say about the Cauchy-Riemann equations. Anyways, okay, so we set u equal to u1, that's a superscript 1, it's not an exponent, plus I times u superscript 2, where I is, of course, a square root of negative 1, and we introduce the typical convention of complex numbers, z equals x plus iy, where z, x, and y are vectors. Then x, the vector in terms of, say, coordinates u1 and u2, is equal to vector x in terms of just u, which is equal to the real component of the vector z of u. So that is, I've said before, I thought that that was a calligraphic character, but it's a German character. But that R is what I'm referring to there, and it just means the real component of this complex valued function. Oh, and here it says where Germanic R of z is the real part of z. In consequence of the Cauchy-Riemann differential equations, x1 equals y2 and x2 equals negative y1. There's another way to state the Cauchy-Riemann equations. That's probably what I wrote down. Oh, there it is. It's underneath my cat, so I can't really read it right now. But we obtain dz du equals x1 minus ix2, where those indices are actually subscripts now. And therefore, the scalar product of dz du with itself is equal to the scalar product of vector x sub 1 with vector x sub 1, then minus 2i times the scalar product of vector x sub 1 with vector x sub 2, and then minus the scalar product of vector x sub 2 with vector x sub 1, which is then equal to g sub 1 1 minus 2i times g sub 1 2 minus g sub 2 2. Hence, from the assumption that u1 and u2 are isothermic coordinates, refer back to theorem 82.1, it follows that the scalar product of dz du with dz du is equal to 0. Conversely, if x of u is harmonic and the corresponding analytic function z of u satisfies what I just read, the dz du scalar product with itself equals 0, then x of u equal to or equivalent to x in terms of u1 and u2 represents a minimal surface, and u1 and u2 are isothermic coordinates. Indeed, from dz du scalar product with itself equals 0, we obtain that g sub 11 equals g sub 22 and g sub 12 equals 0. That is, u1 and u2 are isothermic coordinates. Becoming a little redundant here. Since the Laplacian of x equals 0, or since we have Laplace's equation in effect here, we thus find that the mean curvature capital H is equal to 1 over 2 nu, then times the scalar product of n with the Laplacian of x. This is then equal to 0. So we have mean curvature equal to 0. It's a minimal surface. Let P of u and Q of u be arbitrary functions regular in the domain under consideration. If we set dz1 du equal to p squared minus q squared, dz2 du equal to I times quantity p squared plus q squared closed quantity, and dz3 du equal to 2 times pq, then that scalar product of dz du with itself being equal to 0 is satisfied, since scalar product of dz du with itself is equal to the square of the quantity p squared minus q squared, then minus the square of the quantity p squared plus q squared, then plus 4 times p squared q squared. This is all equal to 0. When integrating the derivatives of the components of z with respect to u, as shown above, the dz1 du, etc., we obtain the following representation of a minimal surface of class r greater than or equal to 3. First, we have x sub 1 equal to the real component of z sub 1 equal to the real component of the integral of p squared minus q squared du. Then we have x sub 2 equal to the real component of z sub 2, which is equal to the real component of the integral of I times the quantity p squared plus q squared closed quantity du. And then we have, finally, x sub 3 equal to the real component of z sub 3, which is equal to the real component of the integral of 2 times p times q du. Now let us assume that p is non-zero and the derivative of q over p is non-zero. That is, p times q prime minus p prime q prime is non-zero. If p is equivalent to 0, or if q over p prime is equal to 0 or equivalent to 0, then we would obtain a plane. So that's why we're making those assumptions. Nevertheless, we set t equal to q over p. Then that means that we have du equals a fraction of p squared over a denominator of q prime times p minus p prime times q. Then that fraction is times dt. Setting capital F of t equal to p to the fourth over a denominator of q prime times p minus p prime times q, we obtain from the representation of the minimal surface component-wise x sub 1, x sub 2, x sub 3, it's those real components that I had just previously read, we obtain from that a formulation or a representation of what are known as the formulae of Weierstrass, but it's also known as the Weierstrass-Enneper representation here. Published in 1866. The representation here, there's another one that you can find on like Wikipedia, or if you do a search online that takes 1 or 2 seconds, I'll put it up on the screen, the alternative representation. But anyways, we have a problem here that's coming up, and okay, I haven't even read the representation that's in the book. Okay, so we have x sub 1 equals the real component of the integral of quantity 1 minus t squared closed quantity, then times capital F of t dt. Second, we have x sub 2 equals the real component of the integral of I times the quantity 1 plus t squared closed quantity, then times capital F of t dt. And finally, last but not least, third, x sub 3 equals the real component of the integral of 2 times t times capital F of t dt. Okay, that's one way of doing it. I'm not going to read the alternative representation out loud. I just want to get to the point here. I flashed a representation on the screen. So, okay, we've got functions f and g involved here, right? If you take f of z equal to 1 and g of z equal to e of z, then guess what? We get a catenoid. Conversely, if you take that function f of z to be I, and you take the other function g of z to be e of z again, then guess what? You get a helicoid. So I feel like that might make this worth it. Anyways, these formulae enable us to associate a minimal surface x in terms of t1 and t2, where the t's have superscript indices, to every regular function where capital F of t is not equivalent to 0, of the complex variable t equal to t1 plus it2, where, again, the indices are superscripts. We finally mentioned that the Weierstrass Enneper representation that is given above can also be written in a form free of integrals, setting capital F equal to h lowercase h triple prime, and integrating by parts. We find x sub 1 is equal to the real component of, we have this quantity which is the difference of two integrals. The first integral, we have integral of lowercase h triple prime of t dt minus the second integral, which is the integral of t squared times h triple prime of t dt, closed quantity. This is then equal to the real component of h double prime of t minus t squared h double prime of t plus 2 times the integral of t times h double prime of t dt, closed quantity, etc. Hence, x sub 1 equals the real component of quantity 1 minus t squared closed quantity times lowercase h double prime plus 2t times lowercase h prime minus 2 times lowercase h. Next, we have x sub 2 equals the real component of I times the quantity 1 plus t squared closed quantity then times lowercase h double prime minus 2i times t times lowercase h prime plus 2i times lowercase h. And finally, x sub 3 equals the real component of 2 times t times lowercase h double prime minus 2 times lowercase h prime. And the last problem, problem 82.1, prove that if capital F equals I over 2t squared, the right helicoid, given as the tangent of x sub 3 equals x sub 1 over x sub 2, is obtained from the Weierstrass Enneper representation. The solution of problem 82.1. We have that x sub 1 equals the real component of the integral of quantity 1 minus t squared closed quantity then times I over 2t squared then dt, which is equal to the real component of negative I over 2 then times the fraction with the numerator of 1 plus t squared over a denominator of t. If we insert t equals t sub 1 plus I times t sub 2, we obtain negative I over 2 then times the fraction with a numerator of 1 plus t squared over a denominator of t. Then this equals negative I over a denominator of 2 times quantity t1 squared plus 2 plus t2 squared closed quantity. Then this fraction is times the quantity 1 plus t1 squared plus 2i t sub 1 times t sub 2 minus t sub 2 squared closed quantity, then times another quantity t sub 1 minus I times t sub 2 closed quantity. Hence, x sub 1 equals t sub 2 over 2, then times quantity 1 minus 1 over a denominator of t1 squared plus t2 squared closed quantity. And similarly, x sub 2 equals negative t sub 1 over 2, then times the quantity 1 minus 1 over a denominator of t1 squared plus t2 squared closed quantity. Therefore, x sub 1 over x sub 2 equals negative t sub 2 over t sub 1. Finally, x sub 3 equals the real component of the integral of I over t dt, which is equal to the real component of I times log of t, which is equal to the real component of I times the entire quantity of the log of the absolute value of t plus then I times the arctangent of t2 over t1, close all quantities, which is then equal to the negative arctangent of T2 over T1. Or using from the problem from the previous section, 81.2, which is just conveniently here on the same page, I guess, we have that tangent of negative x3 is equal to the negative tangent of x3, which is then equal to t sub 2 over t sub 1, which is equal to negative x sub 1 over x sub 2. Wow. We did it, you guys. We made it to the end. It's only 6:20. I'm very hungry. There's no way I'm going to be able to edit this by the end of today. So, like I said, I'm going to edit this tomorrow, get it out to you guys. See you in the next one. We're almost at the end of this book. Kind of not. There's like probably 12, 14 more sections to go. It's technically the longest chapter in the book. But anyways, see you guys in the next one. Peace.